Hello everyone. Today we are going to study metrology or study of measurements. In this chapter, we are going to study the definition, purpose of error analysis, kinds of error, instrument limit of error, statistical error, significant figures, and propagation of error. Definition. What is measurement? It is process of finding the value of a physical quantity experimentally with the help of measuring instruments. The result of measurement must always be a concrete number expressed with proper units of measurement. And purpose of measurement is to find the true value of a particular physical quantity. Suppose I want to find length of a duster and let's say it is 10 centimeter. Should we call it measurement? No. Why? Because I did not use any measuring instrument. But suppose I use a common scale to find the length of a duster and it comes out to be 11.5 centimeter. Then that is called measurement. Here 11.5 is a concrete number and the centimeter is its unit. You will not say 11.5 kgs. Assumptions in finding true value. It exists, it is constant, and true value cannot be found, and it should ideally reflect both qualitatively and quantitatively corresponding property of the object. So why true value cannot be found? Once again, there is error in the instrument that we are going to use, and there is error in reading the scale properly, and the last one, an instrument cannot measure smaller than its least count. Suppose I want to measure the height of the door. Then what will you do? You will get an instrument, something like measuring tape, and you will say that the height of the door is 250 centimeter. And somebody brings a better instrument and he says the height of the door is 250.1 centimeter. And somebody can bring even a better instrument and he can keep on increasing the number of decimal places. But at the end, you cannot go beyond angstrom. And even if you did that for a door, it is of no use. But the main point is that true value cannot be found. Precision versus accuracy. I am choosing an example to explain this. Suppose the value of G is 9.532706 meter per second square. Now this is very precise because the number of decimal places are large. But it is not at all accurate because it is far away from the true value. G equals to 9.7 meter per second square is accurate, although not precise. Now, why this precision and accuracy are important? Suppose you are selling gold and let's say the rate of gold is rupees 3000 per gram. Now you have two balances. Balance 1 reads 1.6431 and balance 2 reads 1.6 gram. So using which balance would you like to sell? Obviously balance 1 because you are getting a better return. So that's why for something like gold, precision becomes very important because even a little change in the second decimal or third decimal places will change the value per gram to a very large amount. So what to talk about 1 kg? But something like making a door, we don't require a precision this high. Let's see another example. This is a dart example and the center of dart represents the true value. Now this is good accuracy and good precision. Why good accuracy? Because it is near the center of the dart. And good precision because all the measured physical quantities are close by. While in the second case, if you notice, the measured points are close by, therefore it is precise, but it is away from the center, therefore it is not accurate. While in the third example, it is all around the center of the dart, therefore it is accurate, but because the measured physical quantities are far apart, these dots are far apart, therefore it is not precise. While in the last one, neither it is precise nor it is accurate. Let's see another example of precision versus accuracy. I have taken 3 instruments: meter scale, slide caliper, screw gauge. Now meter scale reading is 100.0 plus minus zero point 0.1 centimeter, slide caliper is 1.00 plus minus zero point zero 0.01 centimeter, and screw gauge is 0.10 plus minus 0.01 millimeter. So I am finding relative error in all the three, and as you can see, for the meter scale, the relative error is the least. Therefore, it is very accurate. While for the screw gauge, the least count is the minimum among all the three instruments. Therefore, screw gauge is the most precise instrument among all the three. Purpose of error analysis. It is to allow scientists to estimate how large these uncertainties are, help him to reduce them when necessary. Suppose a carpenter wants to make a door for a classroom. Then he need not go for a least count of the order of micrometer. Suppose he goes for the instrument which has least count of micrometer, then the cost of making the door is going to be very high. But instead, if you use a simple measuring instrument like measuring tape, then the cost of making the door is going to be less. But suppose you want to make the doors of bank, then you don't need carpenter. In that case, you need an engineer. And in that case, least count of micrometer for a measuring instrument is justifiable. Comparison of two numbers. In a momentum conservation, we have studied if the initial momentum is equal to the final momentum, then the momentum is said to be conserved. But when we are experimenting, things are not that easy. Suppose two cars are colliding on a frictionless track, and suppose I find the initial momentum. So initial momentum is 1.49 kg meter per second, but the problem is there will be some uncertainty involved with it. And let's say the final momentum is 1.56 plus minus 0.06. What is meaning of 1.49 plus minus 0.03? That means the range is from 1.46 to 1.52, and for the second case, the range is from 1.50 to 1.62. So if you see carefully, from 1.50 to 1.52 in both the cases, the initial momentum is equals to final momentum. So what we say is that since initial momentum is equals to final momentum in the calculated range of uncertainty, therefore momentum conservation is verified. We will never say it is proven. We cannot prove it. If the overlap continues for almost all set of measurements, then we can conclude that momentum is indeed conserved. For some exceptional cases, we do not get consistent result. We remove that data, calling it bad data, or outlying error, or gross error. Note that our experiment does not prove conservation of momentum, and no experiment can. Correct usage of error and uncertainty. Saying that uncertainty is plus minus 1% is right. Or to say that error falls within a range of plus minus 1% is also right. Limit of error is plus minus 1% is also right. And error is plus 1% is also right. But it is wrong to say error is plus minus 1%. Why? Because error cannot be simultaneously on the positive side and negative side. So instead of using the word error, we use the word uncertainty. Error is a slight difference between the measured and the true value. When the difference becomes large, it is called mistake. Mistake or blunder implies carelessness, inexperience, and confusion in the mind of observer. As such, errors are not mistakes. You cannot eliminate them by being very careful. That means error will always be there. Kinds of error: systematic error and random error. Systematic error has definite direction and a definite magnitude. Either it is positive or it is negative. It will not be positive and negative simultaneously. It has assignable cause. That means you can determine what is the cause of error. For example, we studied vernier caliper and we had positive error and negative error. They are systematic error. It was on the positive side or on the negative side. It cannot happen that the vernier scale 0 is to the right of main scale 0 and simultaneously on the left of the 0. So either it is going to be positive or it is going to be negative. It can be eliminated, as we have done in the case of vernier caliper. It cannot be revealed by repeating the measurements. No matter how many times you use the vernier caliper to measure, but unless you find the positive error or the negative error, you will never know for yourself that there is a systematic error in it. Random error. The word random indicates that they are unpredictable and have no definite direction. Its arithmetic mean is 0. It can be minimized by repeating the measurements several times, but it cannot be eliminated. Almost all measurements are subject to both random and systematic errors. The random error is large if the spread in the experimental value is large, and the systematic error is large if it is on one side of the true value. Now let's understand the random error and systematic error with the same dart example. And as we know, the center of the dart is the true value. So in the first case, all the values are around the center of the dart, therefore the systematic error is small. And all these values are close by, therefore random error is small. In the second case, because all the values are away from the true value, therefore systematic error is large, but because they are close by, therefore random error is small. In the third case, all the values are around the true value, therefore systematic error is small, but because they are not close by, therefore random error is large. And in the fourth case, both are large. Now this is a very good way to explain systematic error and random error, but there is one problem here. In real experiments, if we are doing for the first time, we do not know what the truth is. For example, you know the value of g is 9.8 meter per second squared for Earth. But somebody who does not know, and when he starts doing, whatever results he gets, he will think that to be the true value. So in real experiments, what we see is actually this. I hope you understood the point. Now in the first case, what has happened? Random error is small, but systematic? We do not know. Why? Because we do not know the truth. In second case, random error is again small, but systematic? Again we do not know. And in the third, random is large, and in the fourth, random is large. And systematic? We do not know, because we do not know the truth. Systematic error is therefore hard to detect. True value is finally defined as the mean of observed value. Conclusion. K measured is K best plus minus del K systematic plus del K random. Our aim will never be to find the error in the error of a physical quantity. Our aim is always to limit the error to such a level that we can make devices for practical use. Instrument limit error. The purpose is to evaluate the magnitude of uncertainty in the instruments. We will assume that systematic error is already taken care of. So we are discussing random error only in the upcoming sections. Different instruments have different criteria for estimating uncertainty. One is the instruments where repeated measurements is not required, and the second is instruments requiring repeated measurements. And for that we use statistics. For example, what do you think the reading is? It looks around 92 millimeter. Because I am thinking it is around 92 millimeter, therefore I am quoting the uncertainty to be around plus minus 0.5 millimeter, because the least count of the instrument is 1 millimeter. So the probable range is 91.5 millimeter to 92.5 millimeter. Or to say the reading is 92 plus minus 0.5 millimeter. But this is not the complete explanation, because when we are saying the reading is around 92, what about the 0? We cannot really guarantee that we have put the other end of the pencil at exactly 0. So just as the error exists in reading 92, the error exists in reading 0 also. Therefore, chances of underestimating or overestimating at 0 and 92 are same. So 0 millimeter could have been at minus 0.5 millimeter and 92 millimeter could have been at 92.5 millimeter. Thus the worst possible error will be 1 millimeter. Therefore we be pessimistic and write the maximum possible error. So instead of claiming the uncertainty to be plus minus 0.5 millimeter, we will say that the uncertainty is 1 millimeter. because the error exists in reading 92 and error exists in reading 0. So 0.5 plus 0.5 makes 1 millimeter. So the final reading is 92 plus minus 1 millimeter. So now I am going to talk about various instruments where repeated measurements are not required. So in voltmeter, the error occurs because of reading. As we have seen in reading vernier caliper, we are not able to read properly. V best is V final minus V initial, same thing as common scale. Just as error exists in reading the final value, it exists in reading the initial value. So therefore, the maximum possible error is the least count of the instrument in this case. Optical bench. I want to read V and I want to read U. So I'll take the reading here and I'll take the reading here and I'll subtract them. So the error in reading V is going to be the least count, and similarly the error in reading U is going to be the least count. Now we shall try to understand when repeated measurement is required and when it is not required. In case 1 and in case 2, we have several readings. What is the difference between the two? Least count in case 1 is 1 second and least count in case 2 is 0.01 second. We are going to compare these least counts with the reaction time of human being. So let's discuss case 2 first. Can a human have reaction time of 0.01 second? No. Studies have showed that even the best of athletes reach the reaction time of 0.4 seconds with great difficulty. While doing an experiment, human error is going to be more than 0.4 seconds. And stopwatch is offering a small error of 0.01 second. Which is more? Of course, the human error. So, a greater human error is already introduced in the system. So, a smaller error offered by least count is of no use. Or to say in other words, we are going to take the greater error. Also, human error is random in nature. Thus, there is a need to repeat the measurement several times. So in case 2, reaction time is more than least count. Therefore, error is the average reaction time. We shall certainly see later how to calculate it. While in case 1, the instrument's least count is 1 second, which means least count is more than reaction time. Thus the error in the time is least count. Also, when we experiment using such a stopwatch, every time we end up getting the same best estimate as no human error is introduced. Thus repeated measurement is not required. The conclusion is that we be pessimistic and quote the maximum amongst least count and reaction time. Significant figures. What is significant figure? A digit is significant if it is measured by measuring instrument. For example, m equals to 540 plus minus 1 gram. It has 3 significant digits. 540 plus minus 10 gram, it has 2 significant digits. Why that is so? When you are saying it is plus minus 1 gram, you are also saying that you have measured this 5, you have measured this 4, and you have measured this 0 also. Otherwise, why will you say it is plus minus 1? So the last 0 is uncertain because you are saying the uncertainty is plus minus 1. It could have been 9 or it could have been 1. Therefore, this 0 is also significant. And 5 and 4 are definitely significant. So there are 3 significant figures. While for the second case, when you are writing plus minus 10 gram, you are saying this digit 4 is uncertain. And you have never measured this 0. Because you have never measured this 0, it becomes insignificant. And therefore, 5 and 4 are the significant digits. So therefore, we have 2 significant figures in this. Now what about somebody who quotes the measurement to be 540 gram? This is not the proper way to quote, because when you are making a measurement, you always quote uncertainty. But in case somebody forgets to do that, so what we will do, we will be pessimistic and say that the significant figure is 2, considering this 0 to be insignificant. Or It is not measured by the measuring instrument. Suppose the population of city is 157,872. So what are the number of significant figures in this? 6, is it not? But there is a problem with this. Somebody who is saying that the population of this city is 157,872, I think it is highly impossible to really quote the population of city till the last person, because many people will take birth during the time he has measured the population, and many people will die, many will enter the city, many will leave the city. So instead of saying that the population of city is 157,872, so it is good to say that the population of city is 1,57,000. And the number of significant figures is 3. Now suppose you are finding length of a land and somebody quotes this number. If you notice, there is a dot at the end of the 0. Because there is a dot at the end of 0, these 3 zeros are considered to be significant. And therefore, there are 5 significant figures in this one. 1.58 into 10 to the power 5. 3 significant digits. 1.0000, 5 significant digits. Because after the dot, all the zeros that you are putting, you are also saying you have used the instrument of that caliber. So these 4 zeros and a 1 makes 5 significant digits. But suppose there is no dot, then only 1 is significant, all these zeros becomes insignificant. And in the same number, if there is a dot, there are 7 significant figures. Now what scientists intend when they are developing these significant figures, that on unit conversion also the number of significant figures should not change. So what they do is they make the rules according to their convenience. For example, 1.0 centimeter has 2 significant figures. 1.0 into 10 power minus 2 meter also has 2 significant figures. But I can also write 1.0 into 10 power minus 2 as 0.010 meter. Now somebody might claim there are 3 significant figures, but we should understand that it is a convention made by scientists that there are only 2 significant figures, and this 0 will assume to be insignificant. And you can understand, you can write this and this. Now all these zeros are insignificant, making 1 and 0 as significant. So 2 significant figures. So can you guess the number of significant figures in this? 2, 7, 2, 7, 3, 3, 3. Rules for rounding off. 85.6342 plus minus 0.04. The rule is that only after seeing the uncertainty you will quote the best estimate. Although my sentence is very clear, people get confused. Once again, the rule is to see the uncertainty, because that is the chapter. The rule for uncertainty is that there should be only one significant number in this. We round off the best estimate. We do not round off the uncertainty. 0.04. After the decimal, on the second number, that is 3, that is uncertain value. So the uncertainty exists in this 3. So we will round off this number 3. To round off 3, we will see the number after 3, which is 4. So the answer is going to be 85.63 plus minus 0.04. Let's take another example. 85.636 plus minus 0.04. Once again, we'll round off this number 3. But after 3, we have 6. So we'll write this as 85.64 plus minus 0.04. Once again, in this case, we will round off 3. But the problem is we have 5. So instead of seeing 5, we see 51, which is more than 50. So we write 3 as 4. Now in this case, we have 3 and now we have 50. So So the rule is make it even. This 3 is odd, so when we make it even, it is 4. If instead of 3, we had something like 6, which is even already, we'll leave it even and quote the answer as this. Now what about this one? Once again, as I said in this point, that first we will see the uncertainty, and uncertainty should have one number. The problem is, in this, we do not have one number. I also said that you do not round this off. So what we do? We be pessimistic in this. So being pessimistic, instead of writing 0.02, you will write 0.03. And this is not rounding off. We never round off uncertainty. Why 0.03? Because we take only one number in uncertainty. So we will reject 385. And now it is 0.03, and in the best estimate we do not have any number after this 6. So we will leave the answer as this. To understand this further, let's see more examples. Like this one. This is 30. Seeing this, we talk about best estimate. 30 means this 5 has to be rounded off. So to round off 5, we see what is on the right of 5, and that is 1. So the rule of rounding off says that this 1 will become 0. And the answer is going to be this. Let's see another one. 8.123456 plus minus 0.0312. Now the problem is that this uncertainty has a lot of numbers. So what we do, only one significant number will exist here, and rest of will remove. So I'll remove 1, 2, and instead of 3, I'll be pessimistic and write 4. But when you write 4 here, that is second number after the decimal, we'll go to the second number after the decimal, and that is 2 here. So we'll round off this 2. So I'll see a number after 2, which is 3. So we'll leave this 2 as it is. So the answer will be 8.12 plus minus 0.04. Let's see another one. And you know what? This is right. The last one. Now the problem is we have 10 to the power minus 7 here, 10 to the power minus 9 here. So we will make 10 to the power minus 7 here, and this will be 0.03. So if it is 0.03, we will round off this 7. This 7 will become 8. So the answer will be 5.68 plus minus 0.03. Thank you.